Temperature and density. So temperature can be measured on the Kelvin scale, the Celsius scale, or the Fahrenheit scale. There's also another kind of scale called the Rankine scale. I've only read about it. It's not commonly seen. You'll probably never hear about it again. Kelvin is a system which uses the absolute zero, as its starting point. 0 Kelvin is at absolute zero as a temperature. Absolute zero is the concept of the minimum possible temperature, and samples cannot be cooled below such temperature, according to the laws of thermodynamics. Kelvins are not degrees Kelvin. A Kelvin is a unit by itself. So degrees Kelvin is not correct. Don't use it. You will be tempted to use it. I have slipped many times and said it, and I will probably slip and say it again, but don't do it, please. Celsius is degrees Celsius. That is correct. And 0 degrees Celsius is the freezing point of water. 100 degrees Celsius is the boiling point of water. To convert between Kelvin and Celsius is really easy. You just add 273.15 to your Celsius temperature, and that will give you your temperature in kelvins. Similarly, if you have your Kelvin temperature and you want to move to Celsius, you subtract 273.15 kelvins. So simple. An example would be if you have a sample at 25 degrees Celsius, and you would add 273.15 degrees Celsius, multiply by 1 Kelvin, and divide by a degree Celsius, and that will give you 298.15 Kelvin. And this is the standard temperature of laboratories. So kinetic molecular theory is what describes temperature. So temperature arises from movement of molecules and atoms, and the movement of these atoms and molecules gives rise to the phenomenon of temperature. And furthermore, the temperature is the average kinetic energy. So there are molecules at lower kinetic energy and higher kinetic energy, but if you average them, the average kinetic energy is the temperature. So density is a quasi-related concept. It depends on temperature many times. So you'll find that the density of water at 100 degrees Celsius and the density of water at 0 degrees Celsius are very different, but it's the ratio of mass divided by volume. This is kind of strange because mass and volume are both extensive physical properties, and their quotient is an intensive physical property. You can use this formula given two pieces of information to find the third. So you can find the volume of silver if you have a mass of 2.365 grams and a density of 10.5 grams per cubic centimeter. You can set up a nice little equation here where the grams cancel in the numerator and denominator, and you're left with cubic centimeters in the numerator, and that gives you 0.225 cubic centimeters of silver. So that's how you use that formula. It's pretty elementary. States of matter, describing things on a molecular level. You have gases, liquids, and solids. Solids are solid because the molecules and atoms which compose the sample do not move relative to one another. So if I have a crystal lattice, the atoms do not move from their fixed places, but they do vibrate about their position. But no overall net movement. Glass, like glass windows, are a solid. No matter what people have told you about them being a liquid or fluid that are just very thick, it's not true. They're solid. I don't know what I can do to prove it, but it's true. Liquids are special because they stick together. The atoms and molecules which compose a liquid still stick together and are very close to each other, but they move past one another. So they move relative to one another, but they are still close together. Gases are very spread out and are not close to one another, so two gas particles should not be close to one another, and they move around with the highest amount of kinetic energy. So they're going very fast, they're very exciting, they bash against the walls of their container and against each other, and that's That's where the phenomenon of pressure comes from, but different discussion, different chapter. Mixtures are a combination of two compounds or two substances, typically a solvent and a solute. So they can be either heterogeneous or homogeneous. Heterogeneous solutions, hetero being different, so different particles, distinguishable perhaps would be a good way to think of it. It would be like sand and water. You can see the sand particles and you can tell that there's water in between, so they're different concentrations throughout. Homogeneous, homo being same, so it's same throughout. So if I dissolve salt in water, I can't see the salt particles and I can't tell that there's water in between them, so they're homogeneous, it's the same throughout. So there's no distinguishable difference from one part to the next, so long as it's well mixed and completely dissolved. Measurement. An important concept in science, because without measurement we would have no observations, and without observations you cannot prove your hypotheses to be theories, so not good without measurement. So qualitative observations are those which do not use numerical descriptions, so things like yellow, blonde, large, small, the red car. It's an inexact description, and it's open to interpretation. So the user can interpret red to be cherry red or more of a maroon or pink. That's not what science hopes to get. Quantitative observations are much more useful from the scientific perspective because they use numerical information and are exact in their nature. So, for instance, if I tell you that I have 40 kilograms of sugar, you can't say that 40 kilograms is up to your interpretation. 40 kilograms is 40 kilograms. It's just true, it's a number, it's very exact, and that's why science is based upon quantitative measurements and observations rather than qualitative, because it's universal in its applicability, and it's much easier to study quantitative than qualitative observations. Dimensional analysis is a super useful method for moving around units. So say I have a quantitative observation in one unit and I would like to move it to another unit. So for instance, units of lengths here. If I have 1 meter and I know that that is equal to 100 centimeters, then I can use that information in dimensional analysis to convert 400 centimeters into 4 meters by use of a conversion factor. And a conversion factor essentially makes use of the fact that 1 meter is equal to 100 centimeters, and that you can multiply any expression by 1 and then divide it by an equivalent number, and that will give you a expression which is equal to the first expression. So the whole thing works because the numerator and the denominator of my conversion factor are equal to each other. So conversion factors are very easy in that way, and you want to arrange it so that the denominator matches the unit I'm trying to cancel. So here I have 400 centimeters, and I've matched that with 100 centimeters in the denominator. And this gives me the correct answer of 4 meters.